So let me remind you what we want to do. This is the microlocal lift. We have an eigenfunction on the surface for the Laplace. We will let the eigenvalue and the eigenfunction vary so that the eigenvalue goes to infinity. And we are constructing a new eigenfunction for the Casimir on the unit tangent bundle, that's the phi twiggle, so that after possibly choosing subsequences so that everything converges, the measure you get on the unit tangent bundle projects down to the old measure, and the measure on the unit tangent bundle is invariant under the geodesic flow. And there were some things to discuss in between. And this was then the end of the last talk, where we wrote the eigenvalue in this form. We denoted the original eigenfunction as phi naught. That's the trivial lift. That's how a function on the surface can be considered as a function on the unit tangent bundle. But this trivial lift doesn't give you the invariance property, so we need to define these other things inductively. And we saw before that these numerators here, denominators, make these functions again normalized. They all have L2 norm 1. And that comes from this formula, which in return comes from this formula that relates the Casimir and the raising and lowering operators, which is an easier calculation with matrices. Right, now this is the lift. Every single one of these phi 2n's that we defined, every single one of them has norm 1, and they all behave completely different with respect to the k. That makes them all orthogonal to each other. Like the characters on the torus are orthogonal to each other. These phi 2n's on the unit tangent bundle are orthogonal to each other because whenever you integrate over a whole period of k, a whole orbit of k, you get 0. You don't have to integrate over x, just over a single k orbit, and you get 0. Hence, the L2 norm of the sum is precisely what I divide here by. Hence, the phi twiggle is again L2 norm equals 1. There's something else I wrote here on this slide and I forgot. These two formulas, we defined them inductively. So this formula for n greater equal to 0 and this formula for n lesser equal than 0. Using the same relationship between the raising and the lowering operators and the Casimir, you actually show that these formulas hold for all n's. Something one can check, it's the same formula in the end that you will use to prove that. Okay. This is the first of the two theorems that we need. This theorem says when you take your function on the surface with the eigenvalue lambda, and you take a function on the surface, then you can integrate the function with respect to the lifted phi twiggle. That's the averaged over weight lifted phi twiggle. And what you get is essentially the integral that you had before with an error that depends on n and r. So what is r? R was defined by lambda. It's essentially the square root of lambda in size. What is n? I haven't told you. It's some number that we'll define, and that's how many different weights we want to use in the definition of phi twiggle. This phi twiggle always has norm 1, independent which capital N we use. But we will have to figure out the right size of capital N. N equals 0 is too small, that's the trivial version of lifting. And if the N is sort of out of scale with respect to the lambda, then probably this thing will also not behave correctly. So we need to figure out at which scale this lift will have the properties that we desire. And this is the first property that we desire, namely that the lifted measure and the original measure are essentially the same thing. This is an effective statement. That's sort of before you go to the limit. But if you go to the limit and you let your phi vary, then this converges to mu twiggle. This converges to mu. And if we can choose the n so that n times r inverse goes to 0, then we have the lifting property that we wanted. Here I write down a different formula, which will be important. Namely, it's sort of a mixture. This phi is the phi naught, that's the non-lifted function. This expression here is the phi twiggle except for the normalization, right? The normalization sort of magically disappeared in this formula. And the claim is that this formula holds for every k-finite function with the smooth and compact support on the that's a typo. On x. When you say k-finite, I need to have x because a function on M is also k-finite. It has pure weight 0. It's invariant. So that here should be an x. And this is the first of the... This is sort of helping us later to establish the invariance. That's why I'm interested in this. But it's sort of related to this thing because when the f is of weight 0, then there's some easy property that I didn't write down before. When you have a weight n function, that means you know how the function behaves when you apply an element in k, and you have a weight m function, you know how it behaves on the k again, and each time the n or the m are important. Now take the pointwise product of these two functions, and what you get is something that is again of pure weight, but of course the eigenvalues they sort of add, meaning the weights. The eigenvalues multiply, the weights add. So this is the Nice effect, and that helps you to analyze this expression in the case where f has weight 0. If f has weight 0, then f times phi 2n has weight 2n. When you take the inner product of that with phi 0, which has weight 0, you get 0 except when n is equal to 0. Right? So this more complicated looking expression is actually this thing up there. If the f is a function on the surface. So the only thing we really want to prove is that line here. Never mind that the errors are slightly different. That's more detailed than I want to be here. So let me indicate why this theorem holds, why you can switch from integration f with the weight phi twiggle squared, or the density phi twiggle squared, where you can exchange this to the integral f times the sum in the product with phi 0 up to some errors that we will control. That's what I want to explain. So the phi twiggle, let me write it here, is the normalized sum of the phi 2n's. Right? So when I do the phi twiggle squared, I get a 1 over 2n plus 1, okay, because I have the square of what I have up there, and then I have the sum of the inner products of f phi to n, phi to m, and m over the appropriate from minus n to m, n. So if we can make this more look like this, then we are happy. I mean, I want, this should be phi 0, then we would be happy because that's what I claimed. So maybe there's some relationship that allows me to look at this expression and change n and m at the same time and not make too much of a mistake when I do that. So that's why I'm looking at the inner product of f phi to n, phi to m. And now I recall the very definition of the phi to n. I mean, there were these defining equations, defining formulas that I claimed hold for all n, these things. So I just use it, say, for the first expression here, for the phi to m, and I will get confused unless I stick to what I have written there. So it's phi to m, phi to n, 1 over something, f e plus applied to phi to m minus 2, comma, phi to n. So I just used the formula that relates phi to m and phi to m minus 2, and there's some normalization which is one of these expressions here. Now, what I want to do is I want to move the E plus over, because I know what the adjoint of the E plus is. But it's not, the E plus is only defined, applied to one of the two factors, right? So let me do this a bit more carefully. And apply the E plus to both. So the pointwise product of phi with 2m minus 2. And then subtract the term that comes up from the product rule, which is E plus applied to f, pointwise with 2m minus 2, phi 2n. And this is all happening inside the parentheses, so there's this 1 over r in front, which is a good thing because r is big, because lambda is big, so 1 over r is small, and that's good. Now, f is a fixed function, smooth with compact support, even k finite. So this here has some finite infinity norm. So that means that this L2 function of L2 norm 1 multiplied by this bounded function has some bounded L2 norm, and so by Cauchy-Schwarz this whole inner product is bounded by some expression that depends on the function f. But it's independent of the eigenvalue. But in front there's an r, so I can write 1 over IR plus the same thing that I had initially, times the inner product f phi 2m minus 2 minus E minus applied to phi 2n plus O f 1 over r. I did two things. Now that the E plus is applied to an expression, I can move the E plus over because I know it's adjoint. I get this expression. And there's some other terms here, but the imaginary part of what I have in the denominator is r, so it's definitely 1 over r or smaller. So I get this term from that term. And now I need to compare what e minus phi 2n is in relationship to this formula. So I can just look it up. I can now express e minus phi 2n in terms of phi 2n minus 2 and this number here, which then pops up here in the numerator. And there's an n up here if I do that, but below there's an m. So the numerator and denominator are not quite the same. Maybe I make it precise now and write down what I do get by combining it with the formula over there. What I get is that f phi 2m phi 2n is equal to, there's this minus from the minus e minus, there's a minus ir because this constant comes from the second component in the inner product, so of course it's sesquilinear, that this conjugation pops up, plus 1/2 minus n, ir minus 1/2 plus m, and then I have this f phi 2m minus 2 phi 2n minus 2 plus this error term of 1 over r. And there are many minuses, so it's good that now with the many minuses there actually is no minus, so that the numerator looks more like the denominator. And what I get is f phi 2m minus 2 phi 2n minus 2 plus, and now I need to look at what the difference is between numerator and denominator, and it's n minus m divided by this r plus stuff times this inner product plus the old error term of 1 over r. Again, the f is bounded, right? The f is bounded. So this is bounded. So this expression here is bounded, and there's an r in the denominator. Of course, this time we may worry a bit about the numerator, because there's n minus m there. But actually it's not so bad, because if the n and m are very different, if they're far apart in weight, then the whole inner product is equal to 0, as is this one. So we don't need to worry about the error terms because everything is 0. Why is that? Because the f is k-finite. It has only finitely many weights. And because of this product relationship between an and am, if the n and m are further apart than the weights that appear in the f, everything is 0 and I'm happy. And if the n and m are closer together, then n minus m is a constant that depends on f, once more. So this whole term here is again a constant that depends on f divided by r. So this term is the same error term, so I don't have to write it twice. Now, this formula is nice because it does precisely what we wanted. It relates the expression that we had to look at when we wanted to understand the left-hand side here, which is this expression. It relates this expression to this expression because it tells us how we can change the indices at the same time, right? If we change the indices here at the same time, we can make them both smaller by 2 up to an error. And we control how often we have to do that. and then we get this equation. Let me see whether I can say a bit more. Yeah, I think I want to stop here and leave this now. This is the major step. Now you have to sum over the n's and the m's and worry a bit about this term accumulating, but then there's also, we also divide once more by the 1 over 2 n plus 1, so it works out. So this is the corollary. If we define the n in such a way that the n times r inverse goes to 0, then because of the first portion here, the lifted measure that we get is really a lift. It projects down to the old measure. I said that before. Okay. Here we are using that expression, the second expression of the other theorem. Right? This integral is what we are interested in. That's what we want to understand. Because it's really telling us the integral of the function f with respect to the microlocal lift, if in the limit. But this expression is, according to that theorem here, almost the same as this mixed inner product. And here we look at this mixed inner product. And there's a statement. So we take a function, smooth compact support, k finite, and we assume that the n is big enough, but f is fixed, the eigenvalue goes to infinity, and n we will define as a function of the eigenvalue. So once the eigenvalue is big enough, n is sufficiently large as a function of f. That's satisfied. Then the claim is that this vanishes. What is this? H is what we know. H is the differential operator in the direction of the geodesic flow. V is some new fixed degree 2 differential operator, independent of lambda, r, n. It's just some guy that one can work out. And the claim is that this, when you apply r times h plus v to some unknown function f, compact support, k finite, and so on, then this expression isn't just vanishing asymptotically, it's vanishing. And that's a very nice miracle, because this v is fixed. If you apply this v to a fixed function, you get some fixed function. And hence you get some expression that is again bounded. So the vf, together with the inner products here, is a bounded function, is a bounded expression. But the r goes to infinity. So how can this be? If we divide by r, we get to see that h applied to f has asymptotically vanishing integral. This is what the physicists would call the measures invariant. If you take the weak star limit now of along a sequence, we know that this expression is precisely this expression up to some error, right? But this converges to the integral of that function with respect to the measure. So what the other theorem and this theorem together say is that integral h applied to f d mu twiggle is equal to 0. It's saying that even effectively, so before you go to the limit, you have error terms and so on. But now we just go to the limit, we have this statement. This is what the physicists would call the measure is invariant. And in the notes you see a short calculation that tells you that even for an ergodic theorist, yes, this is invariance. It's again one of these instances where you have a statement for an element in the Lie algebra, and then this relates to a statement for the group action. And it's also sort of, what you do is you just apply the fundamental theorem of calculus, essentially. If you know that the derivative is 0 all the time, then you know that the integral is not, the integral is equal to the same at the end, at the two endpoints. So you're looking at the constant functions, so in particular the function at time 0, which is the integral that originally is equal to the function at time t, which is the integral of the function moved by time t. It's very straightforward. There are some technical things about this k-finiteness here, but it all works out. Okay, so this is a small miracle, this first portion. The second portion is a corollary of the first portion of the theorem. So this I want to explain a bit. So the proof uses things that we have talked about before. There is this relationship between the raising and lowering operator and the Casimir, which maybe I write down. No. Just keep going as I have it here, otherwise I get confused. In general, the relationship between the Casimir and the raising and lowering operator is more complicated, but if I apply this to the function phi 0, then I just get Laplace applied to phi 0, which is the Casimir applied to phi 0. Because the difference between the Casimir and this are some w's, w squared and w, but phi 0 is weight 0, so the w doesn't do anything to the phi 0. So that's a trivial thing. The other thing is, I said it, but maybe I haven't written it down so precisely. Originally we know that the Casimir is the Laplace. The Casimir applied to phi 0 is equal to lambda phi 0, right? And then we defined the phi 2 using the E plus, right? The E plus phi 0 essentially up to a constant that is important gave us the phi 2. And what is the Casimir applied to that? Well, we know that the Casimir is in the center of the universal developing algebra. It's not moved. In particular, it's also commuting with the first order differential operators. So it doesn't matter in which order you write this. So you have, this is equal to E plus Casimir phi 0. But that's lambda phi 0. So you get lambda E plus phi 0, which again up to the constant is phi 2. So I said it, but this is the formal reason. All the phi 2n's are eigenfunctions of the Laplace with the same eigenvalue. It's just because the Casimir is in the center. And this we will use. And I want to introduce a shorthand because there's always this function sum from n equals -1 to n, phi 2n. I want to introduce a shorthand for that. Psi is equal to n equals -n to n, phi 2n. Just so that I don't have to write that much. It's just a sum that we kept seeing frequently. There's also something else that we noticed before, which are essentially the recurrence formulas that I want to write down in a different way now. I apply E plus to the psi, which means I apply the E plus simultaneously to all the phi 2n's. Then I don't get just a constant the relationship needs to take into account the n because the normalization was always taking into account the n. But I have another function that takes into account the n, which is just the w. So one can check that you get that this is equal to IR minus 1/2 W minus 1/2 applied to psi, which isn't quite true. There's something else that happens, but that something else is irrelevant for us. What else happens? Well, the weights shift, right? So the sum is then not a sum any longer from minus n to n, but it should be a sum from minus n plus 1 to n plus 1. Because E plus changes the weights. However, these things that are far out will be irrelevant for what we are going to do, because we are taking the inner product of that multiplied with f, inner product with phi 0. So these boundary terms, they are orthogonal to everything we are looking at anyway. So I don't want to make all the formulas more complicated by writing down the correct expressions, because it's difficult enough. So I will use this formula, ignoring the boundary issues. Boundary issues for the summation here, right? For the sum from minus n or minus n plus 1, that is irrelevant. Right, now, how do we start? We start writing down the inner product of f with this psi, multiplied with this psi, inner product with phi 0. We know this is sort of the mixed term, which is related to the integral of f. That's an interesting expression, but we multiply that with lambda. Lambda is a real number, so we can move this lambda in here. And lambda is the eigenvalue of phi 0, so we can introduce here in this expression the Casimir. Voila, very good. Now, the Casimir is self-adjoint, so we can move the Casimir over to this side. So we get Casimir applied to f multiplied with psi, comma, phi 0. Now use, no, sorry, already messed up. I want to start like this, but I don't want to continue like this. Then I recall what I said before, that for phi 0, the Casimir and the E plus E minus are strongly related, so I can replace the Casimir with E minus, which order? E minus E plus. It's the same thing, because the real formula would involve the W's, but the W's are 0 applied to phi 0. And now I move this over to here. And this slide is ugly, so I start a new one. So we have lambda f psi phi 0 is equal to E minus applied to E plus applied. Yes, there are two things that happen when you move it over. The order changes and the plus and minus change, but that makes it the same thing anyway. So there's also two minuses appear that disappear simultaneously. So this is the formula. And this is, yeah, apply this to this product, and then take the inner product with phi 0. We have a product of two functions, and we have differential operators applied to that product. So obviously we have to do the product rule. Obviously we have to do the product rule twice, because we have two differentiations in a row. So we get a collection of terms. Yeah, so sometimes a mathematician has to calculate that alone. So here's a case where we really have to work a bit. So one possibility is that the E minus and E plus are both applied to the F. That's one possibility. One possibility is that the first differentiation E plus goes to the F, but the second differentiation goes, there's a psi. But the second differentiation goes to the psi. That's a possibility. Another possibility is that it's the other way around. And another possibility is that none of the two differential operators derive the F, but they both derive the psi. And then, after all that, you take the inner product with phi 0. Now, there's another step. Where you use this formula that I told you when I introduced the psi. Right, the psi is the sum, and the E plus applied to psi has some formula. And when you do this, here there's an E minus, so it's a slightly different formula. When you do this, you get I R plus I over 2W minus 1/2 psi. And then there's the symmetric term that I didn't write here, which is E minus F IR minus I over 2W minus 1/2 psi. And then there's this term, which I also want to write differently, plus F times, because I know E minus E plus, that's strongly related to the Casimir. There's this W in that I need to bring in so that they're actually equal. So there's Casimir plus 1/2 W composed with W plus I over 2W applied to psi. So if you are still paying attention, then it was good, because now there's something that we should notice. And that's the nice thing that happens. That's the important nice thing that happens. We started with this term. Then comes a huge mess. But in this huge mess, we see this expression, Laplace applied to psi. What is Laplace applied to psi? It's lambda psi. So one term on the right-hand side is F lambda psi inner product phi 0, which is precisely what you started with on the left-hand side. So that's one miracle. Yes. So we started with this term, we produce a huge mess, and in this mess we see precisely this term once more. So we cancel this term. And these two expressions are actually the only expressions that involve the lambda. The lambda is the biggest term. The next important terms are those terms that involve the r. R is about square root lambda. So we look again, where are the r's? There's an r here, and there's an r here, both times in front of the psi, but just as a scalar. So the psi is not, I mean, these guys we need to deal with later, these guys we need to deal with later, but this guy and this guy, they're good. And we could combine these two terms, of course, together with what we see here, and write I E plus plus E minus applied to F psi inner product phi 0. So I'm just picking out these two terms. Write them in one way, but there was this before completely useless relationship between the E plus, the E minus, and the H. The sum of E plus and E minus, just because of the very definition. When you take the sum of these two things, the off-diagonal terms die out. What remains are diagonal terms. So the sum of these two gives you an H. Too far. Which is what we wanted to see. We wanted to see R times H. Here we see the R times H because we see the sum of E plus and E minus, and what I didn't write is the R. So I need to write the R. And then we have the R times the H applied to the F. And now there's this remaining mess. What we want is that the remaining mess is all just a fixed differential operator applied to F. Because then this is the corollary, and then the invariance of the microlocal lift is the corollary. It doesn't yet have the correct form. So let me tell you why. This has the correct form. This is part of V. This goes into V applied to F. Because that's a fixed differential operator applied to F, hit with psi, multiplied just an inner product with phi 0. That's precisely as we wanted it. What's not okay is this guy and this guy, because these guys are applied to psi and not to F. So there is some other miracle that is quicker than the one we saw before. If you take W applied to phi 0, then you get 0, no matter what you write on the left-hand side, because phi 0 is fixed, W takes the derivative, you're getting 0. So suppose you have here a product of two functions, f1, f2, and you take this product of the two functions and then the inner product with W phi 0. You definitely get 0, but we also know that we can move the omega over, the W over, and we get minus 0, which is still 0. W omega, no, W, applied to f1 times f2, inner product phi 0, which is the same by the product rule as WF1 F2 plus F1 W F2 phi 0. Which is nice because it tells us that if we see two functions and their product, where in one of the, okay, so what is this saying? This is saying in a way differently written that W F1 F2 inner product phi 0 is equal to minus F1 W applied to F2 phi 0. It looks like the adjoint formula, but it's sort of all happening in the left side of the inner product. And it's very special for taking inner product with phi 0, and it's very special for W. But that's precisely what we see here. We have W applied to psi, and instead we can move this W without cost to the F. And this guy also. And then these things that are coming from this guy again become part of the V applied to F. And the 1/2, it's fine already anyway, because E plus can become part of the V. So after collecting the mass, you can collect everything else into this new differential operator applied to F, multiplied with psi in a product with phi 0. And the other things are precisely what we wanted to see. Good. So that means we are done with the micro-local lift. We really obtained this theorem. There were two things claimed, namely that by doing this construction of these new eigenfunctions, where you sort of average over the weights, you get these functions that when you take the limit of the distribution, the mass distribution of the new eigenfunctions on the modulus, on the unit tangent bundle, and you then project down to the surface, you get the old limit, but the new limit upstairs is invariant under the geodesic flow. Those were the two claims, and we obtained them after some work. So, I still have a few minutes. Right, so this is the new topic. We established for the micro-local lift invariance. We proved the existence of the micro-local lift and so on. Now we need to talk about the Hecke operators, because the Hecke operators give you this additional, probably unnecessary, but this additional assumption that goes into the theorem that we want to prove. So we haven't even explained all the assumptions in the theorem, because we have seen them, of course, but now we see them also in my talk. So the classical definition of the Hecke operators is as follows. You take the modular surface, you take a prime, you take a function on the modular surface, and then you define a new function. I use a different normalization just because I like probability measures, right? We really average over p plus 1 terms, so I wanted to average. But just a constant, so. You can also just take the sum, which we will also do later. So this is the Hecke operator. What we would like to know is that this Hecke operator is again a function on the modular surface. I mean, the TPF of Z has the same periodicity as the function f had before. But we will see this not via this formula, but a bit later via a different formula. So that's the classical expression. The second definition uses PGL2R instead of SL2R. So what's PGL2R is you take the general linear group, not caring about the determinant, and then you consider two matrices equivalent if they differ by a scalar. That's PGL2R. What's PGL2C? Again, you take the general linear group in the integers, not caring whether the determinant is plus or minus 1, and then you divide out from that minus the identity, which is the only scalar in GL2C, and you get the group PGL2C, which naturally sits inside PGL2R, and you get the space PGL2R mod PGL2C. Now, what's that got to do with what we discussed before somehow? Well, the space PGL2R, which looks a bit more complicated, mod PGL2C, is nothing but the same thing as what we discussed before. R here, SL2C. One way to see that is the following. The right-hand side is the same thing as unimodular lattices in R2. By which I mean, take for instance the C2. C2 I think of as the standard lattice in R2. Its co-volume is 1, that's what I mean by unimodular. And then you multiply this by an element in SL2R and you get something else that has a parallelogram as a fundamental domain, but the volume of this parallelogram, the area of this parallelogram is still 1, so it's still a unimodular lattice. Now, this is sort of an orbit. By considering all of these expressions, I consider an orbit of SL2R. What's the stabilizer of the point C2 under the action of SL2R, meaning which elements in SL2R send C2 back to C2? Well, it's SL2C, so this is an abstract, completely abstract general isomorphism, because that's an orbit of that where this is the stabilizer, so obviously it's correct. This side is equal to lattices not caring about their volume, lattices in R2, considered equivalent if they differ, if I can obtain one from another by multiplying by a scalar, up to homophaty equivalence. Now, again, you can argue very concretely, algebraic, to see that these two things are the same. Now, these two spaces are the same because when you have a co-volume 1 lattice, you can scale it to a different co-volume, but you can't change it and still have co-volume 1. So no two things here become equivalent in here unless they were already the same thing. And every lattice in R2 you can scale in such a way so that its co-volume is equal to 1. So the natural map from here to here is onto. So these two things are the same thing. And that helps us because we can now write down this formula here, which is this second formula for the Hecke operator. We take an equivalence class of lattices. That's the bracket lambda on the left-hand side. And then we look at all the index P subgroups of lambda, which are the lambda primes. And we take the sum over all these, over the values the function has on these index P subgroups. And that defines us a new function evaluated at the point lambda, at the point equal to the equivalence class of lambda, right? The lambda goes here and then is used on the right-hand side to explain at which points we want to evaluate the function f. And then we take an average over p plus 1 points, and this is a definition. That it's the same thing as the old one has to argue. And I may or may not do this tomorrow, I will decide at some point. Thank you for your patience. Yeah. Yeah, up to this scalar difference, they're the same thing, yes. As I said, I like probability measures, so when I define something as an averaging object, then I want to average. But I'm not a number theorist, so I don't have to work with the eigenfunctions or the eigenvalues as